I'm just gonna do Hollow Knight and continue my second full playthrough. And I'm gonna be watching Picasso's. I made an evolutionary. What? I made an evolution simulator with silly little guys. So yeah, let's get it.
Awesome source, and with technology, we can use it to explain our wonderfully weird world. So let's create our own weird world with some little creatures, a type of life simulation to explore evolution and natural selection, look at how DNA mutations can be used to explain different traits, and experiment with different predator species and environmental conditions for our silly little friends. This is a gooblet, and now it's dead because it didn't get enough food and water. These are the only two things that gooblets need to survive because they're very simple creatures and only have one brain cell. They're literally me. So whenever a gooblet's thirst stat gets below a certain level, it's going to start searching for a body of water to drink. I programmed this so that it checks if there's already any water in its sight radius, and if not, it'll choose a random point and fill the water. It'll keep doing this until it becomes so thirsty it dies, or it'll be able to find a water source and be well. The same thing goes for hunger. When it gets too hungry, it'll search for food that grows on these bushes and then waddle away to continue living its life. And that's our starting point. I ran 100 simulations of a single gooblet, and 99% of the time, they were able to survive. The one that died was actually too busy wishlisting my upcoming game, Stinger. Wait. So let's fill our world with a bunch more googlets, because right now, having only one gives it all three sources it ever needs, so we require some competition if we want to make this interesting. We know that water is infinite, so hundreds of googlets can drink from the same source without running out.
Alright, I need to go.
So I massively overestimated how many googlets could survive in this environment. There clearly wasn't enough food to go around, and so a lot of googlets ended up dying at the beginning, as we can see from this massive downward spike when they got hungry. But over time, it begins to flatten out, and on average, we get about 10 googlets living in harmony together. Now, since the googlets can only live and die, the total population is going to decrease. So what if we gave them the ability to get funky? If a male and female googlet are both well-fed and well-watered, they can decide to have a baby. I'm not quite sure how this works because, if we have red and blue parents, we can approximate that the googlet offspring will be purple, with some variation either side. So it could be more like its mum or more like its dad. So this is the general concept of reproduction, or as we call it in Australia, mating. Adding this functionality into our simulation allows us to see that the population does decrease at first when our gooblets get hungry and all the food gets used up. But it rises slowly when the gooblets that do survive can mate and then fluctuates around a stable level, which in this case is about 20. In fancy biology language, we can call this number the carrying capacity, as it's the maximum number of gooblets that the environment can sustain. And as you might expect, if we simply add in some more bushes, we can keep a greater number of gooblets alive. It means there's more food to go around, so more gooblets can live together, which pushes our carrying capacity up to about 40-50ish. So it's not only determined by the creatures, but also the environment that they live in. I also found it interesting that if we start with 10 gooblets instead of 100, we still end up with the same carrying capacity. And I guess that's just because neither the gooblets
I'm just doing this to get some money.
change. But this is still pretty simple. Each gooblet is practically identical, so I added some varying variables which can vary in its variability for speed, making each gooblet zoom faster to wherever they need to go, sight range so they can see things further away, and the number of children that they produce. Now when two gooblets have kids, their offspring will have stats that are an average of their mum and dad's stats. So if one super fast and one super slow gooblet get funky together, their children will be pretty mid. And we're going to add or subtract some random value in these stats to account for genetic mutations. We'll look at this later in the video, but for now, this is just some random variation between gooblets. So now when we run the simulation, we can see how the average traits change over time, and even with the simple behaviors given to these creatures, we get quite complex results. We see that in this environment, it's better to have more children per generation, probably due to there not being any active threats to the gooblet race. speed and sight both increase given enough time, which means we're getting more gooblets which are faster and better sighted. Now, in hindsight, this is probably what we should have expected, because they can get to food and water quicker, allowing them to survive better and reproduce. And what we've just shown here is Charles Darwin's theory of natural selection. Over time, the population will evolve with new traits to match the environment, and we continually approach the optimal gooblet. These gooblets have a better chance of surviving, and therefore reproducing, passing its traits onto its children, and producing more optimal gooblets until something changes in the environment, which we will explore right now. Let's make two similar environments. They will have 2 ponds and 6 bushes each, except one is very small and condensed, and the other is a lot more spread out. So the only difference here is the size of the world. If we place 100 identical gooblets in each of these environments, we actually see a considerable difference in their evolution. In the small world, gooblets don't actually need to evolve better traits because even the weaker ones can survive. The resources are so close to them that it doesn't matter if they're slow or blind, because they'll still be able to reach them and reproduce. But when we spread out the ponds and bushes further, the weaker gooblets aren't able to track down food and water as easily, so it's a lot more important for gooblets to evolve quicker and stronger in this environment, because resources are just more difficult to find. So if they don't evolve quick enough, eventually the gooblet population will go extinct. And in a lot of simulations, this is what happened, and in some cases, a single gooblet hung on for a long time. But what they didn't realize is that they were alone, in an empty, simulated world. Their existence out of their control.
Oh, we got a Duolingo ad. Duo.
Celebrate the holidays at home.
Just like everyone on my Discord server. These are how speed and sight evolved in the smaller environment where it wasn't as crucial for gooblets to develop better traits. You can see that it does sort of increase, which makes sense, but when we compare it to the larger environment, you can clearly see the difference that this one change made. The selective pressure of not having as much food and water led to faster and overall better evolution for these gooblets, especially for the sight range, which proved to be very important. And remember, we started with the exact same number and strength of gooblets in these simulations, and they just act differently based on how spread out their food and water was. It's also interesting to note that for any simulation, we won't see many changes right at the beginning, because it still takes time to show if these evolutions are beneficial. And just for good measure, here are the graphs for the number of gooblets and number of children produced in both environments, and they do kind of have some interesting correlations, but nothing super important. Quick side tangent. For those interested in programming and game development, the gooblets essentially have a state machine where, based on their hunger and thirst, will either be looking for food, looking for water, looking for a mate, or if they've just gotten funky, they'll remain chill until they need to find more food and water again. And this is pretty much the way I coded this entire simulation. Another quick side tangent. You may be watching this video and saying, iCalso, you have all of these graphs and data, but you could just be making them up. Well, listen here, you clever little russet potato. This was my first real dive into data collection and analysis, so what I did was loop through each gooblet that was alive at any one time. Then I added their speed, sight, and kids to a running code to get the average. Then I wrote that data into an Excel spreadsheet, so every time this code runs, it adds a new line into my file. And then I can import this newfangled data into After Effects, and with many hours of trying new things until it works, make an animated graph. You might not care about this as much as I do, and that's fine. I just thought it would be interesting to share, because I'm a silly little guy. Well, right now, speed and sight have 0 downsides. Obviously, if you can be faster and have better vision, you're going to survive better. So there has to be some sort of cost for having these better traits. It's like how taller people need to eat more food because they have more body to support. So I decided that a faster a gooblet is, the more hungry and thirsty it becomes, because it's going to be using more energy to move quicker. But this same logic doesn't really work for gooblets with better eyesight, because it doesn't take a whole lot of energy to just look for these resources. But in biology, sometimes changes to one trait can influence another in seemingly unpredictable and counterintuitive ways, sometimes called pleiotropy. And in the case of gooblets, having a better sight range is going to decrease the hunger.
Stickman Studios. Oh, there's Stickman Studios. Can I climb up here? I can't. Okay. Yeah, I've never tested that. Oops. Hello. Oh. I got ACC. I'm sorry? Wait, are you able to elaborate on what that means? I've never, really, seen a lot of abbreviations. But, I'm not very good with them. Would it be possible for I to elaborate? Wait, what's going here? Okay, Oh. Ah! I keep doing these random things that I know aren't gonna turn out well, but I still do them anyway. Put this up here. Now we're gonna hope and pray. Ow, okay. We're gonna hope that we don't get sniped again. Yep, that's not gonna work. That's not gonna work! That's not gonna work! I just got the Black Egg Temple. Halamagoska. I'm bored. I'm gonna run it. $91. Holy crap, I'm so close. Okay, we're gonna go. Alright, we gotta lock in, gang. Oops. No, I'm in. Bro. Alright, we're here. Bro! I've won 12 this game before. I'm the fade! Bro! Sucks. Yeah, we're not doing that. Dude, that was like an undodgeable pattern. Yeah, we're not doing that right now. No. 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 We're not doing that. We're doing this one. We gotta get some practice in. It's been a while since I've played Hollow Knight or Hollow Knight Silksong. Alright, we're just gonna do the average build in Call of 3. Alright, let's do it. Cats. Quacks, 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 quacks. Stop!
Stop, Chase, hey, so, go, 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 go. Stop, taking my butts.
Oopsies.
Stop taking my butts.
No! Stop it! Stop! Wow, get that guy out of here. Stop it!
So, taking my butts. What?
The average Silksong enemy?
Yellow, Teddy, yellow.
Whoa! There's no way! Am I this powerful? I'm way too powerful. I don't got this! Stop punching me! Stop! Ah! Hello. Oh my god. We gotta stop. Stop. Okay. Just take a breather. I so. Oh, finally. So. Stop! Oh my god. Alright, boss. I'm getting. Oh. Oh my god. Stop spawning enemies! Let me heal! Sorry, yep, okay, yep, I'm sorry, sorry, no problem. Oh my god, yeah! I'm so happy. Oh, oh. Okay. Yeah! Get out of here, you Gabo! What? Sola, Nico. Yeah! Oh my god, I have a puppy. I have a puppy right here. Puppy. Ew! And more. Bro, you gave me so much less than last time. We're switching games.